All right. Any other homeworks coming in? All right. So any questions on the homework?
How would you explain the final problem?
What was the final problem?
If n times n is odd, prove n is odd.
All right, let's see. So let's prove that if n squared is odd, then n is odd. This is one of these that works really well with an indirect proof as opposed to direct. And so you would first want to know something else which you proved in a previous problem, which is prove if n is even, then n times n is even. Okay, so let's just prove that. If n is even, n is equal to 2 times some integer, and so n times n equals 2 times k times 2 times k equals 2 times k times 2 times k, and this thing here is an integer, so n times n equals 2 times an integer, therefore n times n is even. So that's a prior problem. But now let's prove this original. Prove that if n times n is odd, then n is odd. Well, suppose n times n is odd. Well, we're starting off with n times n is odd. Suppose n is not odd. All right, so we're going to contradict the hypothesis. That means n is even. But then by this theorem that we just proved, n times n is also even. And that's a contradiction of what we started with, which is n times n is odd. So assuming the negation of the hypothesis leads us to a contradiction, so the hypothesis must have been true. So n must be odd. Does that make sense? All right, questions on the new homework? So it's 5 questions from 3.8. These are on quantifiers. And then there's a proof involving divisibility, similar to what we were proving on Wednesday. I don't know why this says 40 points, but I'll give you 40 points for it. The double value homework. So no questions on those? Last try, any questions on the programming assignment? All right, well, let's talk about modular arithmetic. So we talked about this idea on Wednesday of divisibility, and we made sort of the observation that if we pick two numbers like 17 and 3, we can write 17 as something times 3 plus some remainder. and that the kind of usual way to do this is to try to put 3 into 17 as many times as possible and then just see what's left over. And if we do that, our remainder is going to be bigger than or equal to 0, but less than 3. And there's a theorem that there's always exactly one unique number with this characteristic that we get as a remainder when we try to write 17 as something times 3 plus whatever's left over. So let me just write that formally. So given positive integers m and n, there exists a unique remainder, which is an integer bigger than or equal to 0 and less than n, such that 17 equals some quotient times, m equals some quotient times n plus the remainder, where q is an integer. That doesn't feel very warm and fuzzy to me, but it's really just saying this. If you take two integers, we can write one as a product of the other times some big number plus a little bit left over, where that little bit left over is, you know, not negative, but as small as it can be. And this is a really useful concept, this remainder. And we're going to mostly work with that for a while. So let me give you a definition. So we can say A is congruent to B modulo M if M divides A minus B. A is congruent to B modulo M if M divides their difference. So for example, 23 is congruent to 17 modulo 5. Because the difference between 17 and 23 is 5, and that's divisible by 5. And we can write congruent with this triple equal sign, so this is no longer logical equivalence, this is congruence. And we sometimes write modulo M as just mod M in parentheses. So we could say 23 is congruent to 17, parentheses mod 5. 23 is also congruent to 12. And I'm just going to be working mod 5 for the rest of this column, so I'm not going to keep writing mod 5 in parentheses. 23 is also congruent to 3. I lost something here. About 18. Because 23 minus 18 is 5. So 23 is also congruent to 3 because 23 minus 3 is 20. 23 is also congruent to minus 2. Why? Because the difference of 23 and minus 2, 23 minus minus 2 is 25. And that's divisible by 5. So if we want to be mathematical-like for a moment, we can note the following things. For any integer x, x is always congruent to itself. Why? Because x minus x is 0, and 0 is divisible by anything. Right? Why? Because it's equal to that anything times 0. We can also note that if A is congruent to B, then B is congruent to A. Why? Because this says a minus b is divisible by whatever modulo you're working over. And this says b minus a is divisible by that. Well, b minus a is just the negative of a minus b. And if 15 is a multiple of 5, then minus 15 is also a multiple of 5. So we get this automatically. This is all modulo m. We also get if a is congruent to b and b is congruent to c, then a is congruent to c. So there's transitivity, there's commutativity, there's what we call reflexivity, saying x is congruent to itself. How do we know that this third thing is true? If a is congruent to b and b is congruent to c, then a is congruent to c. Well, a minus b equals, some integer times m, and b minus c equals some other integer times m. And if we add these two expressions together, a minus b plus b minus c is equal to I times m plus j times m. Well, this left side is just a minus c, and this right side is just I plus j times m. So a minus c is again a multiple of m. So you can spend hours and days playing with these things and prove all sorts of identities, and somewhere along the way someone has to do that to know that this is what we call a valid mathematical system. We can turn this into something called a group, or maybe a field, or an algebra, or things like that. But we're not going to go down that path. But we're going to use this idea of congruence, right? Two things are congruent if they're divisible by, their difference is divisible by whatever modulo we're working in. And there's a different way to think of this. Let's just work mod m. This means a minus b is divisible by m. Well, let's go back to the division algorithm and let's try writing a as equal to, something times m plus some remainder r. And let's write b as something else times m plus some remainder s. If we use these forms to write a minus b, right, I can just plug these forms in. Right, a minus b is m times I minus j plus r minus s. But I've told you that a minus b is a multiple of m, right? And this is a multiple of m. And if you think about it a little bit, you'll convince yourself r minus s has got to be equal to 0. That takes some work to know that it's not a multiple of m itself, but because these things are between 0 and m minus 1, you can convince yourself r minus s is equal to 0. So what does this mean? Well, it gives us this fact that we can just take as given. If a is congruent to b modulo m, then a and b have the same remainder when divided by m. And this is perhaps the more useful way to think about congruence. Two things are congruent modulo m if, when we do this divide by m and see what's left over, they're both going to have the same amount left over. And so what's 23 divided by 5? Well, it's something with 3 left over. 18 divided by 5 is something with 3 left over. right? Same with 23 and 3, or 23 and minus 2, right? The remainder is always 3. That's why these things are congruent. So here's what we're going to do. We're going to invent a new type of algebra. And we know how to add, subtract, and multiply and divide regular numbers. We're going to invent a new set of numbers. And we're going to look at addition and subtraction and multiplication and some form of division on these new numbers. So let's fix some modulus m. So we're always going to be thinking about mod m. So if m is 5, we're thinking about remainders when you divide things by 5. Or we're thinking about two things whose difference is a multiple of 5. Let's replace each integer n with its remainder when divided by m. So m is fixed. It's just some number. We're going to take every integer that we know, there's a whole bunch of them, and we're going to replace it with the value we get when we divide that integer by m. We're going to replace it with its remainder. So let's look at what happens if we do this modulo 3. So if we take 10 and we divide it by 3, what's the remainder we get? If we take 5 and we divide it by 3, what's the remainder we get? If we take 6 and divide it by 3, what's the remainder? How about 0? 4? Right? So you can see what's starting to happen here, right? We keep getting 0, 1, or 2. And we've said a remainder has to be bigger than or equal to 0 and less than 3. These are the only possible remainders we can get. 1, it's actually an easy one, but it can be tricky sometimes. 1 divided by 3. Well, 3 goes into 1 0 times with exactly 1 left over. And 3 goes into 2 0 times with exactly 2 left over. Now what about negative 1? This one's kind of funky. And our intuitive notion of leftover doesn't really work. But let's write negative 1 equals something times 3 plus some remainder. So if I do 1 times 3, that's 3, my remainder is negative 4. That's no good. If I do 0 times 3, my remainder is negative 1. Well, that's still too small. If I do negative 1 times 3, that's negative 1 times 3 plus 2. Well, that's within range. And if I were to keep going, negative 6 plus 5, well, that's too big. So this is really the remainder. So that gets us back to 2. And there's a pattern here. If I look at the things congruent to 2, well, there was 5. Subtract 3 from that, we get down to 2. Subtract another 3, we get down to negative 1. Subtract another 3, we get to negative 4. If we added, we'd get 8 and 11 and 14, and those are all congruent to 2, mod 3. And so there's kind of a cycle here. If we write these down mod 3, right? They're just repeating. So we're going to make a new algebra, and since we're working mod 3, our algebra is going to have the following things in it: 0, 1, and 2, and that's it. And we're going to define addition of these things modulo 3. So 0 plus 0, well, that probably better be 0. If it's not 0, something weird's going to happen. 0 plus 1, that should be 1. 0 plus 2 should be 2. 1 plus 0 should be 1. 1 plus 1 should be 2. But what about 1 plus 2? Right? I mean, it's logically equal to 3, but 3 is not part of our universe of numbers, right? But we've associated 3 with 0, so we're going to make this equal to 0. 2 plus 0 is 2, 2 plus 1 is 3, which again is 0, and 2 plus 2 is 4, which we're saying is associated with 1. So here's how we define addition on this funny set of numbers. So we can do multiplication, and multiplication by 0 is 0, which is nice. Multiplication by 1 just gives us our original number. And then 2 times 2 again is 4, and we can't use a 4, but we're going to use a 1 because that's congruent to 4 modulo 3. So there's how we do multiplication. And we can do subtraction the same way. 1 minus 2 would be negative 1, which would take us back to 2. So nothing really bad going on here. It's just a different way to do things. And this addition is actually something we do almost every day, probably. Especially towards the end of a long class. So that's almost what our clock looks like. I put a 0 in instead of 12. But if it's 4 o'clock and you want to know what time it is 9 hours later, 4 plus 9 is 13. We don't say it's going to be 13 o'clock. We say it's going to be 1 o'clock. Right? So when we do time on a clock and we're looking at hours, we're really working modulo 12. And if you want to know what time it is 100 hours from 4 o'clock, it's not 104 o'clock. Take 104, divide by 12, look at what's left over. That's what time it's going to be. Whatever that turns out to be. I think it's 8 o'clock. And if you're programming in C or Java, we have this operator, a percent sign, which we can use to do modular arithmetic. Percent lets us divide one thing by another and tell us what the remainder is. So that's what's going on here. All right, so here's why this is potentially interesting. Still working fixed sum modulo m. Let a and b be integers. We can take a and b and we can add them together and we can reduce that modulo m and we get some number. Right? We can also take a modulo m and we can take b modulo m and add those together. And this answer and this answer are going to be congruent modulo m. So we're taking the set of all integers and we're moving to a small universe, something containing just a few numbers. And what I'm suggesting here is that we can move to that small universe and then do some addition, or we can do some addition, take the answer, and then move to that small universe. We're going to get the same answer in the end. And that's why we like modular arithmetic. It's going to let us answer questions about big numbers by doing work on small numbers.
Like in cryptography.
Like in cryptography.
RSA.
Yep, exactly. How many people here know about SparkFun?
Know about what?
SparkFun? So SparkFun is a very cool website for electronic gadgets and gizmos. I'm not surprised by that.
Them and Adafruit.
Yeah, Adafruit's also a really good one. So, well, I should have looked at this before. Do you get their Friday emails? SparkFun? Okay.
Yeah. I haven't looked at it today, so.
I seem to have deleted it. Oh, this isn't the one. Anyway, they have a crypto shield for $5 on their website. It's one of this week's specials. And it saves certificates and public-private keys and all sorts of stuff. Anyway, it's in their mailer. There's tons of hardware out there and software that like feeds into all the stuff that we're talking about in here and in the 224, 22, 23 sequence. There's just tons of stuff out there, and it's mostly affordable. I mean, it's a few bucks, and it's really good to play with. There was an article, I think last week, in a newsletter about someone who's making a self-driving lawnmower. It's like a riding mower, but he's putting in like machine learning to let it like drive itself. You know, which is probably safer than a self-driving bus in terms of what goes wrong. But good stuff to play with. All right, so here's what this means. If A is congruent to B and C is congruent to D, then A plus C is congruent to B plus D, and A minus C is congruent to B minus D, and A times C is congruent to B times D. So if all we're interested in is the remainder when you divide something by 17, if we have a bunch of numbers we want to multiply and know what the remainder is when we divide by 17, we don't need to multiply all those numbers together first. We can take each of them and see what they're congruent to mod 17. We're going to get a small number between 0 and 16. We can just multiply those together. So for example, what is the remainder of 123 times 256 times 41,372 modulo 5? So if I want to multiply those numbers together and know what the remainder is when I divide by 5, what's the answer? Well, I can multiply these together and then divide by 5. Or I can say, what's 123 congruent to mod 5? And 5 goes into 10, so if your number ends with 0, 1, 2, 3, or 4, that's what it's congruent to. If it ends with 5, 6, 7, 8, or 9, it's congruent to 0, 1, 2, 3, or 4. So 256 is congruent to, it's going to be one more than a multiple of 5, 255. And 41,372 is congruent to 2. It's 2 more than a multiple of 5, which is 41,370. And if I multiply these together, it's going to be congruent to 3 times 1 times 2, which is 6, which is congruent to 1. So if I do 123 times 256 times 41,372, I get a number that ends with a 6. That's 1 more than a multiple of 5. Okay, is this making sense so far? So we can do stuff with this. There's a big number. I can guarantee this is divisible by 3. Anybody know the trick? You probably know the trick. How do we know that this is divisible by 3?
If the sum of the digits is divisible by 3, then the
If the
number...
sum of the digits is divisible by 3, the number is divisible by 3. And that's a lot of digits to add up, but you know what? I don't actually even need the full sum of the digits. I just need to know if the sum of the digits is divisible by 3. Well, so there's a 4 and a 2. That gives me 6. That's divisible by 3. There's a 6, still divisible by 3. There's a 1, that's 8, that's 9, that's divisible by 3. Divisible by 3, divisible by 3, 2 and 1 divisible by 3. That's enough. This is a multiple of 3. So that's just a little trick that you bump into somewhere. But why does this work? So what is this number? This is actually the number 1 plus 2 times 10 plus 3 times 10 squared plus 9 times 10 cubed plus 1 times 10 to the 4th. I should have made this smaller. Alright, that's what that number is equal to. Divisibility by 3 means congruent to 0 mod 3. So now I'm switching my brain to only think about mod 3, arithmetic. Well, what is 10 congruent to mod 3? Congruent to 1. 10 squared is 10 times 10. That must be congruent to 1 times 1, which is 1. And it is. 10 squared is 100, which is 1 more than 99, which is a multiple of 3. Well, if 10 squared is congruent to 1, 10 is congruent to 1. 10 cubed is congruent to 1 times 1, which is just 1. And in fact, 10 to any integer is congruent to 1.
That's why this also works for 9.
That's why it also works for 9. So if I'm going to work modulo n, I can replace this with a 1, this with a 1, this with a 1, and so on. And so this whole thing is congruent to 1 plus 3, 1 plus 2 plus 3 plus 9. Just the sum of the digits. If the sum is divisible by 3, then the big long sum, which is this number, is divisible by 3. And similarly, if you work mod 9, 10 to the n is still congruent to 1. And so if the sum of your digits is a multiple of 9, then your original number was a multiple of 9. So 27, 2 plus 7, 81, 8 plus 1. So that's another trick. What about mod 10? What what is 10 congruent to mod 10? Right? Its remainder is 0 when you divide 10 by 10. 10 goes in once with nothing left over. So 10 squared is also congruent to 0. 10 cubed is also congruent to 0. 10 to the n is congruent to 0 for any n bigger than or equal to 1. But 10 to the 0, that's just 1. That's just congruent to 1. So in that case, each of these things is congruent to 0 when I multiply by those digits. That's all 0. This number is congruent to whatever its last digit is, mod 10. And we know that, right? If a number is a multiple of 10, it ends with 0. If it ends with a 7 and you divide by 10, you're going to have 7 left over. But that's the reason why it works. All right, one more, modulo 11. So 1 is just congruent to 1. What is 10 congruent to modulo 11? It's really just 10, right? But it's also negative 1. Because the difference of 10 and minus 1 is 11. And 11 is divisible by 11. If we think of 10 as congruent to minus 1, 10 squared is minus 1 times minus 1, that's just 1. 10 cubed is 10 squared times 10, that's minus 1. 10 to the 4th is 10 cubed times 10, that's minus 1 times minus 1 is 1. Right, and 10 to the 0, just to complete the chart, is just 1. So powers of 10 alternate between plus and minus 1, modulo 11. So let's just pick a random number like 2871. All right, so we can write it out as powers of 10. So this is congruent to 1 times 1 plus 7 times minus 1 plus 8 times 1 plus 2 times minus 1, which is congruent to 1 plus 8 minus 7 plus 2. And this is what I get if I take the digits in the odd positions and add them together, and then take the digits in the even positions and add them together and subtract those from each other. And if that difference is a multiple of 11, then your number is a multiple of 11. And if not, then it's not. So that's a really quick way to tell if something's divisible by 11. Add up the even digits, add up the odd digits. If the difference is a multiple of 11, your number is divisible by 11. So these are good party tricks depending on the caliber of party you go to. All right, got the basic idea? All right, let's take a 5-minute break, and then we're going to talk about prime numbers.